Okay, today we're going to talk about the Adair model. This is a really important model for cooperative binding. It's not the only model. We'll also talk about the Hill model, but we'll go through all the details of the Adair model today. So the idea here is that you've got some binding sites. So we've been talking primarily about adsorption of molecules from a gas onto a surface. Here I think we'll talk about, say, some protein. We've got some protein. There's a couple of binding sites. Let's say 4 binding sites. And the question is, if a ligand binds to one site, does it make the other sites more likely to bind a ligand or less likely to bind a ligand? And so you can have either positive cooperativity, where it makes each subsequent binding more likely, or you can have negative cooperativity, where it makes each subsequent binding less likely. Well, the Adair model really goes into the detail of each individual equilibrium and works out the, I guess, a generalized version of the Langmuir isotherm for that. So let's go through that for the example of 4 binding sites. We'll use 4 because it's sufficiently complicated enough that we can see some of the details, but it's still doable in a reasonable amount of time. All right, so how we do this is we set up 4 equilibrium equations. So we've got our receptor plus our ligand goes to our receptor ligand. I'm going to wait here a moment to put the equilibrium constant because there's a little bit to that. Then we have receptor ligand plus ligand goes to receptor ligand now with 2 ligands bound. And we have RL2 plus R goes to RL3, and RL3 plus L goes to RL4. All right, there's an equilibrium constant associated with this. K1, K2, K3, K4. But there's also a statistical factor. And for the case of 4 binding sites, this is 4, 3/2, 2/3, and 1/4. Okay, and we'll see where those come from in just a minute. Now, ultimately, we want a fraction of bound sites. So we're going to try to set this up analogous to the Langmuir isotherm. And so this will be RL plus RL squared. But now we need a 2 here because there's 2 ligands bound. Okay, 2 of the sites are bound. Plus 3 RL3 plus 4 RL4. Because we're looking at the bound site. So if we have one of these, for every one of these, we actually have 2 sites bound. And then we divide by the total number of sites, which is just going to be 4 times the concentration of all of these. So we have the empty site and then each of the subsequently bound versions. So this is what we're going after, and we want to see how we might be able to get it. So we're going to do it with two things we need to do. First, we need to figure out where these statistical factors are coming from. And then secondly, we're going to write down the equilibrium expression and subsequently sort of bootstrap our way from this reaction to this reaction to this reaction to this reaction to eliminate all but the equilibrium constants and the concentration of the ligand. So we want to get rid of all the concentrations of the receptor because those are difficult to measure. Easier to measure the ligand concentration. All right, so let's look at these statistical factors. I'm going to erase this and I'll put it back up again later. And how I like to do this is, if I've got 4 sites, I like to draw a picture of 4 boxes. And on this side, I put where we're starting from. So this is 4 empty boxes because we have the receptor with no bound ligands. And we're going to go to one bound. And then we just write all the ways that that can happen. And what's being assumed here is that all the sites are equally likely for the first molecule, first ligand. And so we see we go from a case where we've got 1 possibility statistically to 4 possibilities statistically. So that's where this factor of 4 comes in to our equilibrium constant. So what this equilibrium constant is the equilibrium constant for like doing this, and then we have a statistical factor of 4 possibilities for that. So that's pulled out of the equilibrium constant. Okay, well let's do it for now the next one. So in that case, we have 1 possible, and there's 4 of these. I won't write all those. Those are the ones we had over here. But now we have 2. One, 2, 3, 4, 5, 6 possibilities. And we're coming from 4, so we have a statistical factor of 6/4 or 3/2. And that's where this guy's coming from. All right, now to get our next one, now we're coming from this state. I'll just leave this here. And we're going to be going to a state with 3. And now we can use symmetry. So having 3 bound and 1 unbound is really the same statistically as having 1 bound and 3 unbound. So we're going to have 4 of these guys. So we came from 6, and we're going to 4. So we're going to have 4, 6. So that's the 2/3 factor that's sitting right here. And finally, to go all the way to fully bound, there's only 1 possible way. We came from 4, so that's going to be 1/4. And so that's this statistical factor right here. So it's good to just play around with this a little bit. Maybe try a case with 3 or 5 and see if you can get the correct statistical factors. All right, so that's one thing we needed to do, get those statistical factors. Now let's set up the equilibrium constants. So here we have 4K1. And so this whole thing is the equilibrium constant, the statistical factor and the actual equilibrium constant for a single binding site of the statistical 4 there in this case. And so that's RL over RL. And we're going to re-express this for RL. like that. Now, I'm going to, oops, I shouldn't be equal here, just arrow here. So this is what we're going to write for each one of these. So I'm going to just write that in here and sort of skip a step and just write it in this form for all of the others. So then this guy is going to be RL2, 3/2 K2, RL L. This one is going to be RL3, 2/3 K3, RL2, RL. And this one is going to be RL4, times L. Now notice here, I can stick the top one into the second one over here, and then here, and here. And that's what I meant when I said we're going to sort of bootstrap our way from one chemical reaction to the other. So if I do that, this one I have RL2 equals 3/2 times 4 times K1, K2, RL squared. So this here is, what is that, 6? So now let's stick that guy into here. So we get so now this is 4. And we can finally stick that into here. And that's just going to be 1. Okay. All right, let's see if I've got some room here. Let me rewrite my fraction of open channels. So that was R plus, or RL plus 2 times RL2 plus 3 times RL3 plus 4 times RL4 all over 4 out front R and just to reiterate again, see where are these numbers coming from? Each individual protein, for example, has 4 sites, and we want the fraction of bound sites. So the concentration of RL is going to tell us, it's going to be related to how many times 1 of the 4 is bound. And here, this will how many times 2 of the 4 is bound, and so on. And then down here, all of these, this is just all the possible sites. So it doesn't matter if a ligand is bound or not, we're counting it. And so that's where we get that factor of 4 in front of everything. So that's where those numbers come from again. All right, let's now substitute these in. RL2 is this. Let's see, 2 times. All right, we're going to run out of room here. Okay, this is RL3. All right, so there's our numerator and our denominator. Oh, I'm missing a R plus RL plus RL2. Okay, now we can do some simplification. So notice, so this is 12. This is 12. So we have a factor of 4 that can be pulled out of the numerator and canceled down here. We also have a factor of r that is in every term. So we can pull out 4r on the top and the bottom. And so this will eliminate all of the r's, leaving only k's and l's, which is what we wanted, and also reduce the numbers by a factor of 4. Okay, and so this is the expression for the Adair model for a 4-binding site, cooperative binding site. And if, so in sort of just a general case where we have positive, increasingly positive binding, that would mean that K1 is less than K2, less than K3, less than K4. And negative binding would be the other way around. So this would be positive cooperativity. This would be negative cooperativity. Now, of course, in general, we could have all sorts of different relationships between the Ks, and not necessarily a steadily increasing K or steadily decreasing K. So it may depend on, it may be a much more complicated system. And so nonetheless, this captures that if we can get the values for the different Ks, which of course would be the experimental challenge of this. All right, in the next lecture, we're going to talk about a simpler model of this that has only one K, called the Hill model, and it will exhibit positive or negative cooperative binding. And then we'll also, in that video, we'll also talk about a measure of, a way to measure how cooperative a model is relative to the Langmuir model, which is a completely independent model.